Good evening and welcome to a new course on the Laplace transform. This will be the second course on this topic, and we'll go over a couple of more examples, new useful properties of the Laplace transform, and how to look at the phenomenon of resonance in the context of the Laplace transform. And next time, we'll continue with convolution, which is also a notion that is intertwined with the Laplace transform and the Fourier transform. To review what we said last time, the Laplace transform is a linear operator which associates to a function, f of t, another function, which is its Laplace transform, which is a function of s, such that LF of s is equal to integral from 0 to infinity of f of t e to the minus ts dt. And this integral is the improper Riemann integral. The Laplace transform is a linear operator, and same for its inverse, L inverse. And so functions are associated in pairs if the Laplace transform of f is LF, then the inverse Laplace transform of LF is f. Laplace transforms of many elementary functions are well known, including exponentials, sine, cosine, natural logarithm, polynomials, and many others. And you can read them from tables like the table in our textbook. And in many cases, the inverse Laplace transform can be computed using the same tables. So we're going to take a rational function, decompose it into partial fractions, and then use the same tables to see whose Laplace transform is each fraction. So what is the inverse Laplace transform of each fraction? There are more general methods like the Bromwich integral, but those methods go a bit beyond our course. The formulas that we'll use over and over again when solving ordinary differential equations by the Laplace transform are the formulas for the Laplace transform of the derivative and of the second derivative, and more rarely of higher order derivatives. So if the Laplace transform of a function lowercase y is uppercase y, so we denote it by uppercase y, then the Laplace transform of y prime is s times uppercase y minus the value of lowercase y at time 0. And the Laplace transform of y double prime is s squared times uppercase y minus s times the value of y of lowercase y at time 0 minus y prime of 0. So notice that when I solve an ordinary differential equation by the Laplace transform, this method automatically takes the initial data into account because they appear in the formula for Laplace transform of the derivative and the Laplace transform of the second order derivative. And similarly, the Laplace transform of the third order derivative would be s cubed y minus s squared y of 0 minus s y prime of 0 minus y double prime of 0. So the Laplace transform automatically somehow takes into account exactly the right number of initial conditions. If you have a second order equation, then it takes into account y of 0 and y prime of 0. If you have a third order equation, then it will also take into account y double prime of 0. So please see this formula in the previous course or in the textbook. And how do we use these formulas? The solution always works in the same way. First, we take the Laplace transform of the ordinary differential equation, which means we take the Laplace transform of the left-hand side and of the right-hand side, and they must be equal to each other. And by using the Laplace transform, derivatives become multiplication by s or by s squared or by s cubed. So instead of a differential equation, we get an algebraic equation. Then this algebraic equation can be solved just by algebraic manipulations. And we get the Laplace transform of the solution. So we get almost immediately an answer, which is the Laplace transform of the solution. And then the final step is that we need to invert the Laplace transform. So knowing the Laplace transform of the solution, we want to compute the actual solution by means of the inverse Laplace transform. So let's start with this example. Let's consider the initial value problem. Y double prime minus 5y prime plus 4y is equal to e to the minus x with the initial conditions y of 0 is 3 and y prime of 0 is 0. So this is a linear inhomogeneous equation with constant coefficients. So actually it's inhomogeneous because we have e to the minus x on the right hand side. Then anyway, this is an appropriate equation to solve by the Laplace transform. So we apply the Laplace transform to both sides of the equation. We get that the Laplace transform of y double prime minus 5y prime plus 4y is equal to the Laplace transform of e to the minus x. Now if this equation had non-constant coefficients, or if this were a nonlinear equation, then it would be harder to proceed from here. But since this equation is linear and has constant coefficients, we can use the linearity of the Laplace transform itself, and then L of y double prime minus 5y prime plus 4y is the same as L of y double prime minus 5 L of y prime plus 4 L of y. So if we had something like y squared, or if one of the coefficients were, for example, sine of x, then we couldn't do this for the coefficients being sine of x, and we wouldn't know what the Laplace transform of y squared is. But as things are for this equation, now, so because the coefficients are constants, we could just pull them out of the Laplace transform. So we have 5 times the Laplace transform of y prime and 4 times the Laplace transform of y. And then we can express the Laplace transforms of y double prime and of y prime as a function of the Laplace transform of y. So we can reduce everything to the Laplace transform of y, because this is a linear equation. So if we had something like y squared, the Laplace transform of y squared is harder to express in terms of the Laplace transform of y. And on the right-hand side, we have the Laplace transform of e to the minus x, which if we use the formulas that we reduced last time, Laplace transform of e to the minus x should be 1 over s plus 1. Right. So let's use the formulas for the Laplace transform of y double prime and the Laplace transform of y prime and convert everything to the Laplace transform of y. So let the Laplace transform of y be capital Y. And then Laplace transform of y double prime is s squared capital Y minus s times lowercase y of 0 minus lowercase y prime of 0. And the Laplace transform of y prime is s times capital Y minus lowercase y of 0. Right? So now in this new equation, after we applied the Laplace transform, the only unknown is capital Y. That is because we are given the initial conditions, so we know what y of 0 and y prime of 0 are. So let's substitute them into the equation. Y of 0 is 3, and y prime of 0 is 0. And we get this equation, s squared times capital Y minus 3s. And then y prime of 0 is 0, so it doesn't matter. And then minus 5 times sy minus y of 0, which is 3, plus 4y is equal to 1 over s plus 1. So this is actually a pretty simple equation in terms of capital Y. It's a linear equation. Let's group all the terms with capital Y on one side and all the terms that don't have capital Y on the other side. So we have 3 terms containing capital Y. We have s squared capital Y, and then we have minus 5s capital Y, and then plus 4 capital Y. And so we group them and we factor capital Y, and we get s squared minus 5s plus 4 times capital Y. And on the other side, we have, so minus 3s, when it goes to the other side, it becomes 3s. And then minus 5 times minus 3 is 15. When it goes to the other side, it becomes minus 15. And 1 over s plus 1. So on the other side, we have 3s minus 15 plus 1 over s plus 1. Notice, and we'll talk more about this probably in the next course, that this polynomial, which is times y, so s squared minus 5s plus 4, is actually the auxiliary polynomial of the equation. Right? So in any case, we have this linear equation, and we have separated the terms that contain y on one side and the other terms from the other side. So now, solving for capital Y, we get that capital Y is 3s minus 15 plus 1 over s plus 1 over s squared minus 5s plus 4. So bringing this to a common denominator, we get that this is the same as 3s minus 15 times s plus 1, everything plus 1, over the common denominator, which is s squared minus 5s plus 4 times s plus 1. And carrying out the multiplication on the top, we get 3s squared minus 12s minus 14. On the bottom, we don't want to carry out the multiplication, we want to factor the denominator. So instead of s squared minus 5s plus 4, we write it as s minus 1 times s minus 4. And then it's times s plus 1, which was a separate factor. So that was the Laplace transform of the solution. It was capital Y, the Laplace transform of the solution. So now we need to compute the inverse Laplace transform of that to get lowercase y, which is the solution of our original equation. So if uppercase y is the Laplace transform of y, then y now is the inverse Laplace transform of capital Y. And our method for computing the Laplace transform of these sorts of rational functions, so a rational function is the quotient of two polynomials, is to decompose them into partial fractions. So we use the same method that we use to compute the integral of these partial fractions, of these rational functions. We decompose them into partial fractions. So the composition into partial fractions depends on the factors in the denominator. So here we have s minus 1 times s minus 4 times s plus 1. So then the decomposition into partial fractions will be some constant over s minus 1 plus some other constant over s minus 4 plus another constant over s plus 1. And the three constants a, b, and c will depend on the numerator. So they will depend on 3s squared minus 12s minus 14. So we need to find a, b, and c such that this rational function 3s squared minus 12s minus 14 over s minus 1 times s minus 4 times s plus 1 is equal to a over s minus 1 plus b over s minus 4 plus c over s plus 1. So the computation, the same one that you may have seen in calculus 2, gives that a is 23 over 6, b is minus 14 over 15, and c is 1 over 10. There are several ways of doing this computation. The most general one is we bring the right-hand side to a common denominator. So that's going to be a times s minus 4 times s plus 1 plus b times s minus 1 times s plus 1 plus c times s minus 1 times s minus 4. And then we try to identify the coefficients of the numerator with the coefficients of the numerator on the left-hand side. So with 3s squared minus 12s minus 14. So both of them would be polynomials, and two polynomials are equal if and only if all of their coefficients are equal. Anyway, so whether you do the computation by this method or by some other method, we get these values for a, b, and c, and then this means that we get a partial fraction decomposition of capital Y. So capital Y of s is 23 over 6 over s minus 1 plus minus 14 over 15 over s minus 4 plus 1/10 over s plus 1. Right? So now we still want to compute the inverse Laplace transform of this, but we know the inverse Laplace transform of each of these simple fractions, and therefore, since the inverse Laplace transform is linear, we can compute the inverse Laplace transform of capital Y. So the inverse Laplace transform of capital Y would be 23 over 6 times the inverse Laplace transform of 1 over s minus 1 plus minus 14 over 15 times the Laplace transform of 1 over s minus 4 plus 1/10 times the Laplace transform of 1 over s plus 1. And the Laplace transform of 1 over s minus 1 is e to the t. Laplace transform of the inverse Laplace transform of 1 over s minus 4 is e to the 4t, and the inverse Laplace transform of 1 over s plus 1 is e to the minus t. So in general, since the Laplace transform of e to the at is 1 over s minus a, then the inverse Laplace transform of 1 over s minus a is e to the at. So, for example, the inverse Laplace transform of 1 over s minus 4 is e to the 4t. And we look at 1 over s plus 1 as 1 over s minus 1. So therefore, its inverse Laplace transform will be e to the minus t. All right, so since we know the inverse Laplace transform of each of these simple fractions, we know the inverse Laplace transform of capital Y. So that's 23 over 6 e to the t minus 14 over 15 e to the 4t plus 1 over 10 e to the minus t. And this is the solution of the initial value problem that we wanted to solve. So first, we took the Laplace transform of the equation. Then from a pretty simple equation, we computed capital Y, which is the Laplace transform of the solution. And then by using the decomposition into partial fractions, we computed the inverse Laplace transform of capital Y, which is lowercase y, the solution to our original equation. So again, it is 23 over 6 e to the t minus 14 over 15 e to the 4t plus 1/10 e to the minus t. So if we think in terms of the previous method that we used, the method of the auxiliary polynomial and undetermined coefficients, then 1 over 10 e to the minus t is the particular solution of the equation that corresponds to the source term. And 23 over 6 e to the t minus 14 over 15 e to the 4t is the complementary term, which is a solution of the associated homogeneous equation. And in this case, so in general, that solution would be some constant times e to the t, and then plus another constant times e to the 4t. But in this case, we could compute the constants, namely 23 over 6 and minus 14 over 15. And we could compute them because we are given initial data. Y of 0 is equal to 3 and y prime of 0 is equal to 0. All right, let's consider a second example. Y double prime minus 5y prime plus 4y is equal to e to the t. Y of 0 is minus 1, y prime of 0 is 5. This example looks almost identical to the previous one, except that instead of having e to the minus t, like in the previous example, and it should have been e to the minus t, so e to the minus x was a typo. One should use t in the context of the Laplace transform, traditionally. Well, so instead of e to the minus t, here we have e to the t. However, as I see, this makes a significant difference because the equation with e to the minus t did not have any resonance, but the equation with e to the t has a resonance between e to the t on the right-hand side of the equation and the linear operator on the left-hand side of the equation. So why is this so? The auxiliary polynomial for this equation is lambda squared minus 5 lambda plus 4, which has roots lambda equal 1 and lambda is equal to 4. So the space of solutions of the associated homogeneous equation is spanned by e to the t and e to the 4t. So one function for each of the two distinct roots. However, the source term for this equation is also e to the t. So as we discussed when talking about the method of undetermined coefficients, if the source term has the same exponential growth or decay modes or the same oscillation as the left-hand side, then it resonates with the system described by the left-hand side of the equation. So we have not yet explained why this happens. The full explanation, maybe we'll have to wait until we talk about convolution. But in any case, so we notice that we are in the case where there is a resonance between the right-hand side of the equation and the left-hand side. So when would we have such a resonance? Any combination of e to the t, e to the 4t, or this times integer powers of t on the right-hand side, so in the source term, would resonate with the left-hand side. So for example, e to the 4t, or t squared e to the t, or their sum, or I don't know, 3 times e to the 4t minus 3t squared e to the t would resonate with the left-hand side. So for the method of undetermined coefficients, that turns out to be a pretty special case, and we need a different guess. Here for the Laplace transform, however, it's somewhat more straightforward. So this is why in such a case, we would rather use the method of the Laplace transform, as you'll see. So let's use the Laplace transform to solve this equation. We apply the Laplace transform to the equation, meaning the Laplace transform of the left-hand side is equal to the Laplace transform of the right-hand side. By linearity, the Laplace transform of the left-hand side is the Laplace transform of y double prime minus 5 times the Laplace transform of y prime plus 4 times the Laplace transform of y. And the Laplace transform of the right-hand side is 1 over s minus 1. So the Laplace transform of e to the t is 1 over s minus 1, as we computed in the previous course. Actually, we also computed this expression L of y double prime minus 5 L of y prime plus 4 L of y in the previous example. So the difference will be what happens because of the 1 over s minus 1. So using the known formulas for the Laplace transform of y double prime and the Laplace transform of y prime, we get that s squared of y minus s lowercase y of 0 minus lowercase y prime of 0. So this is the Laplace transform of y double prime. And then minus 5 times the Laplace transform of y prime, which is s capital Y minus lowercase y of 0. And then plus 4 times the Laplace transform of lowercase y, which is uppercase y. So all of this is equal to 1 over s minus 1. So we're given the initial conditions, and then so y of 0 is minus 1, y prime of 0 is 5, and we can make these replacements. So as I said before, when solving an equation by the method of the Laplace transform, it automatically takes into account the initial conditions at time 0. And we get s squared capital Y plus s minus 5. So it's plus s because it was minus y of 0 times s. So because y of 0 is minus 1, this gives plus s. So s squared capital Y plus s minus 5, then minus 5 times s capital Y plus 1. So again, for the same reason, it's minus minus 1, so it's plus 1. And then plus 4 capital Y is 1 over s minus 1. And again, this is a linear equation in capital Y. And we group all the terms with capital Y together. And we get s squared minus 5s plus 4, everything times capital Y. And then what are the terms that do not involve capital Y? Let's put them all on the other side. So we have an s on the left-hand side, which becomes minus s on the other side. And then we have minus 5 and another minus 5 times 1. So minus 10, which becomes plus 10 on the other side. And plus 1 over s minus 1, which we had already on the other side. So capital Y is equal to minus s plus 10 plus 1 over s minus 1 over s squared minus 5s plus 4. So bringing this to a common denominator, we get minus s plus 10 times s minus 1 plus 1 over s squared minus 5s plus 4 times s minus 1. So in the numerator, when we carry out the computation, we get minus s squared plus 11s minus 9. And in the denominator, s squared minus 5s plus 4 factors as s minus 1 times s minus 4. Then we have another factor of s minus 1, which is already there. So we get s minus 1 squared times s minus 4. So this is how we can tell that there is a resonance in the equation. Namely, it is seen in the fact that the denominator has a root with multiplicity. So the factor s minus 1 squared shows that there is a resonance, because the root s equal 1 of the polynomial s minus 1 squared times s minus 4 has multiplicity 2. So the square shows that we have multiplicity, and the multiplicity shows that we have resonance. And indeed, this comes from exactly what I said in the beginning. So one of the factors came from the Laplace transform of the left-hand side of the equation. So it was present in s squared minus 5s plus 4. And the other factor came from the right-hand side of the equation. So it was present in the Laplace transform of e to the t. And as we'll see, this causes a resonance in the equation. So anyway, we got what capital Y is. So capital Y of S is minus s squared plus 11s minus 9 over s minus 1 squared times s minus 4. And this is, again, a rational function. It's the quotient of two polynomials. And we want to compute its inverse Laplace transform. And in order to compute its inverse Laplace transform, we're going to decompose it into partial fractions. So again, the decomposition into partial fractions depends on the denominator. Since we have s minus 1 squared times s minus 4 in the denominator, then the decomposition into partial fractions will be some constant over s minus 1 plus another constant over s minus 1 squared plus a third constant over s minus 4. And we can compute the three constants, capital A, capital B, and capital C, by looking at the numerator on the left-hand side. So they will depend on this numerator, minus s squared plus 11s minus 9. And notice that this decomposition is different from the one in the previous example, because we have s minus 1 squared here in the denominator. So we have a fraction whose denominator is not s minus a constant, but it is s minus a constant squared. And if we had the root of higher multiplicity, we could have s minus a constant cubed or something even more complicated. So this is the effect of the resonance. We get these more complicated denominators when there is a resonance in the equation. So in our case, again, by bringing the right-hand side to a common denominator and then identifying the coefficients of the polynomial that you get in the numerator, eventually we obtain that B is minus 1/3, C is 19 over 9, and A is minus 28 over 9, if my computations are correct. And then, in order to find the solution, we must compute the inverse Laplace transform of each term. We already know how to compute the inverse Laplace transform of A over S minus 1 and of C over S minus 4. The inverse Laplace transform of A over S minus 1 will be A times e to the power t, and the inverse Laplace transform of C over S minus 4 will be e raised to the power 4t times C. So this follows in the same way as in the previous example. However, we still need to compute the inverse Laplace transform of B over S minus 1 squared. So we need to compute the inverse Laplace transform of 1 over S minus 1 squared. So there are several ways of computing the inverse Laplace transform of these more complicated fractions. And next time we'll see that we'll have a look at the convolution product, and we'll see that it can also be used to compute these Laplace transforms. But this time, let's use this new property of the Laplace transform to compute it. And please also remember that several of these formulas can be found in formula tables for the Laplace transform and for the inverse Laplace transform. But since it's the first time we are seeing this, let's actually compute it. So the formula that we're going to use is that Laplace transform of t times a function of t is minus the derivative of the Laplace transform of f. How do we prove this? This is almost straightforward. So the computation is straightforward. The Laplace transform of f is the integral from 0 to infinity of f of t e to the minus ts dt. And then its derivative is the derivative of this as a function of s, because the Laplace transform of f is a function of s. So we have the derivative as a function of s of the integral from 0 to infinity of f of t e to the minus ts dt. So since the integration limits do not depend on s, and since the integration variable is t, not s, then under some reasonable assumptions on f of t, we can interchange the derivative of and the integral. So the derivative of the integral is equal to the integral of the derivative in this case. So it's integral from 0 to infinity of d over ds of f of t e to the minus ts dt, which is integral from 0 to infinity of, so the derivative as a function of s of the expression of the under the integral. F of t is not a function of s, so it's not affected by the derivative. And then the derivative of e to the minus ts is minus t e to the minus ts. Right? So we get, integral from 0 to infinity of f of t times minus t e to the minus s dt. We can pull the minus out of the integral, so it's minus integral from 0 to infinity of tf of t e to the minus ts dt. And this integral is, by definition, the Laplace transform of tf of t. So this is minus the Laplace transform of tf of t. Right? So now let's do a sample computation with this formula. We know that the Laplace transform of the constant function 1 is 1 over s. So the Laplace transform of t is minus the derivative of 1 over s. Since the derivative of 1 over s is minus 1 over s squared, this means that the Laplace transform of t is 1 over s squared. All right, then doing this several times, multiplying by t, let's say, n times, we should get minus 1 to the n times the nth derivative as a function of s. So if we do this to the constant function 1, then the Laplace transform of t to the n times 1, so the Laplace transform of t to the n is minus 1 to the n times the nth derivative of 1 over s. So if we take the derivative of 1 over s n times, we would get n factorial over s to the n plus 1. and then with a plus or minus sign, depending on whether n is odd or even. So actually it's minus 1 to the n times n factorial over s to the n plus 1. And the minus 1 to the n times minus 1 to the n in front gives us 1. And then we are left with n factorial over s to the n plus 1. And recall that n factorial is part of all positive integers from 1 to n. So, for example, the Laplace transform of t squared will be 2 over, so 2 factorial, which is 2 over s cubed. Laplace transform of, let's see, t to the fourth would be 4 factorial over s to the 5. 4 factorial is 24, so that's 24 over s to the 5. And in the same manner, if we start with e to the power at, whose Laplace transform is 1 over s minus a, then the Laplace transform of t to the n e to the at would be minus 1 to the n times the nth derivative of 1 over s minus a. And by a similar computation, I get that this is n factorial over s minus a to the n plus 1. Okay, so now we also want to compute some inverse Laplace transforms. So then from this formula, we get that the inverse Laplace transform of n factorial over s minus a to the n plus 1 is t to the n over the times e to the at. So this is almost looking like one of the fractions that we want to understand in the partial fraction decomposition. And let's divide everything by n factorial. And since the inverse Laplace transform is linear, we get that the inverse Laplace transform of 1 over s minus a to the n plus 1 is t to the n over n factorial e to the at. So now we can give values to n, and we get that the inverse Laplace transform of 1 over s minus a squared is e to the at. The inverse Laplace transform of 1 over s minus a cubed is t squared over 2 e to the at. The inverse Laplace transform of 1 over s minus a to the fourth is t cubed over 3 factorial e to the at, and etc. So the next one will be t to the fourth over 4 factorial, and so on. So we can compute the inverse Laplace transforms of all these simple fractions that you get in the partial fraction decomposition when there is multiplicity in the equation. And the next step, maybe next time, will be to see what happens when we have complex roots. So when there are sines and cosines in the equation. Right? So for our example, we had to compute the inverse Laplace transform of b over s minus 1 squared. So this is b times the inverse Laplace transform of 1 over s minus 1 squared. And we computed on the previous page that this is t e to the t. So the inverse Laplace transform of this term that we didn't understand is b times t e to the t. Right? So this actually is the effect of the resonance. So the resonance, what it does is that it gives us extra powers of t. So the source term e to the t on the right-hand side of the equation resonates with one of the modes of the equation, which is e to the t. So that is one of the solutions of the associated homogeneous equation. So that is one of the natural modes of the equation. This is how a solution could behave with or without a source term on the right-hand side. So you would always have e to the t. And now e to the t on the right-hand side resonates with that. And therefore, it induces extra growth and gives us a term of t times e to the t. So because of the resonance, this term is bigger than expected. It is t e to the t instead of e to the t. So let's go back to the solution. So the solution, lowercase y, is the inverse Laplace transform of uppercase y. So it is the inverse Laplace transform of, and we computed the partial fraction decomposition of uppercase y, and we got minus 28 over 9 over s minus 1, plus minus 1/3 over s minus 1 squared, plus 19 over 9 over s minus 4. So we get minus 28 over 9 times the inverse Laplace transform of 1 over s minus 1, then minus 1/3 times the inverse Laplace transform of 1 over s minus 1 squared, plus 19 over 9 times the inverse Laplace transform of 1 over s minus 4. So this is because the inverse Laplace transform is linear. This means that the inverse Laplace transform of the sum is the sum of the inverse Laplace transforms. And we can also pull out the coefficients because these are numbers. These are constant coefficients. Minus 28 over 9, minus 1/3, and 19 over 9. So the solution is minus 28 over 9 times the inverse Laplace transform of 1 over s minus 1, which is e to the t, minus 1/3 times the inverse Laplace transform of 1 over s minus 1 squared, which is t e to the t, plus 19 over 9 times the inverse Laplace transform of 1 over s minus 4, which is e to the 4t. So here, minus 28 over 9 e to the t plus 19 over 9 e to the 4t is the complementary term, and minus 1/3 t to the t is a particular solution of the equation. And here, again, we can compute exactly what the complementary term is because we are given initial conditions for y of 0 and y prime of 0. So each mode of the solution, exponential increase, exponential decrease, or oscillations, or some combination of this. So when we have complex roots, as you'll see, we can have a combination of exponential and oscillations. So each mode is represented by a specific expression under the Laplace transform. Namely, it is represented by one of those simple fractions that you get in the partial fraction decomposition. So when doing the partial fraction decomposition, we actually get the decomposition of the solution into the individual modes. So this is actually a very good way of thinking about the problem because it tells us how the solution is made of components that increase exponentially, components that decrease exponentially, components that oscillate, and so on and so forth. Like in the previous example, it was a sum of 3 different components, each of which had a different behavior. And in many cases, this is the easiest way to compute the inverse Laplace transform. So we decompose the solution into partial fractions, and then we look up in some table of Laplace transforms or inverse Laplace transforms. We look up the inverse Laplace transform of each of those partial fractions. And so far, we have seen how to do this for two types of partial fractions. So for 1 over s minus a constant and 1 over s minus a constant raised to some power, which corresponds to resonance. And maybe next time we'll also look at how to do this in the case in which there are complex roots. And with this, we'll know how to compute the partial fraction decomposition and how to compute the inverse Laplace transform of pretty much every function we want to solve this for. And what else? On the previous page, we saw that the Laplace transform tells us directly when there is a resonance in the equation and when there isn't, and it tells us what is the multiplicity of the resonance, so how many modes are resonating together, and therefore what polynomial power of growth we gain. And as we'll see next time, this also gives us some explanation for where the resonance is coming from. We'll try to understand it next time in terms of a convolution problem. So in any case, this time we see that the resonance corresponds to the multiplicity of the roots in the denominator. So whenever you have a root of multiplicity like this s minus 1 squared in the denominator here, this means that we have resonance. And this leads in the system described by the equation to an extra factor of polynomial growth. So resonance amplifies the modes that are resonating together. And hopefully we'll understand this better next time by means of convolutions. Okay, so what is the advantage of using the Laplace transform? What is the reason for using the Laplace transform? Laplace transform is a good way of solving this type of equations. We transform a differential equation into a much simpler equation, namely an algebraic equation, which does not involve any derivatives. We solve this simpler equation, and then we transform back. So it is a radically simple procedure for solving ordinary differential equations. Its importance also partly comes from the fact that it was the first such method that was discovered. It was discovered before the Fourier transform, for example, and so it gave the start to the discovery of a family of methods that are used in similar ways for ordinary differential equations and partial differential equations. The Laplace transform itself is widely used. It is the standard method for solving and analyzing linear constant coefficient equations in several fields, such as electrical engineering. So people analyze circuits in terms of the Laplace transform of the equation of the ordinary differential equations, so describing those circuits. And Another advantage is that it incorporates the initial conditions without our having to do anything extra. So when we take the Laplace transform of an equation, it already takes the initial conditions into account. So we don't need to first solve and find the general solution. It already gives us the particular solution for those initial conditions. And even though the Laplace transform works really well for the equations we solve by means of the Laplace transform, this class is somewhat limited, so it only applies to linear equations with constant coefficients. For nonlinear equations or for linear equations with non-constant coefficients, when we take the Laplace transform of the equation, we can still do it, but we do not get such a simple equation, and we cannot solve it in terms of capital Y as easily as we solve it for linear equations with constant coefficients. So this is the main drawback. It only applies to this class of linear equations with constant coefficients. Otherwise, we can still use it, but it does not lead to an easy solution. However, linear equations with constant coefficients appear all over the place. They're widely used in describing all sorts of phenomena. Therefore, the Laplace transform is a very useful tool. Thank you for your attention, and see you next time.